students, I am Tulika Banerjee. Today, I bring you a learning module in BSc Forensic Science on behalf of the content writers Dr. G.S. Sodhi and myself on an important unit of forensic ballistics in which we will discuss about propellants and their history. We will wind up this module with discussion on color coding of ammunition. We will be discussing here about propellants. The expression propellant means an agent which fires the projectiles out from a firearm. In order to propel a bullet or a shotgun charge, that is pellet or shots, through the barrel and air, a certain amount of force is necessary. The powder charge gets ignited through primer and converts it into a gas very quickly, thereby resulting in the development of high pressure in the cartridge and thereby forcing the bullet to get out of the barrel. The types of propellant used are gunpowder, which is also called as black powder. Then we have smokeless powders, semi-smokeless powders, triple base powders and RDX based propellant. First, we will be discussing here about gunpowder. Gunpowder is the oldest recorded propellant. It was used for giving signals and fireworks. The gunpowder consists of potassium nitrate, sulfur and charcoal roughly in the proportion of 75:15:10. The powder is not suitable for high velocity ammunition as large amounts of powder are required for getting high velocities for the projectiles. The powder leaves a considerate amount of solid residue which tends to foul the barrel. It remains fairly stable if kept dry over prolonged period. It is glazed and polished to increase its storing or keeping qualities. Gunpowder causes much smoke and fouling of the barrel. It is mostly used in muzzle loading weapons and blank cartridges also. The powder is available with different grain sizes having a mesh limit from 6 to 10 to 46 to 60. The second type of propellant is the smokeless powders. The modern high velocity era started with the use of smokeless powders. The basic constituents of the smokeless powders are nitroglycerine and nitrocellulose, which is also known as gun cotton. Nitrocellulose is either used alone or in combination with nitroglycerine to form propellants. The latter are called as double base powders, while the former is known as a combination of a single base powder only. Some of the double base powders that are commonly used contains nitroglycerine. Nitrocellulose and mineral jelly are cordite, modified cordite and ballistite. The composition of common double base powder is cordite has 58% nitroglycerine, 37% nitrocellulose and 5% of mineral jelly. Modified cordite has 30% of nitroglycerine, 65% of nitrocellulose and 5% of mineral jelly for the stabilization purpose. Ballistite has equal quantities of nitroglycerine and nitrocellulose without any mineral jelly. However, the lifespan of such powder has been increased tremendously by improved technology and by addition of stabilizers. It is important to note that smokeless powders do not explode inside a cartridge. Instead, they combust. Since the combustion is occurring in a closed space, it can have the force of an explosion. The third type is the semi-smokeless powders. Semi-smokeless powder is a mixture of black powder and nitrocellulose. The approximate composition of the powder comprises of nitrated wood cellulose 20%, potassium nitrate 60%, carbon 12%, sulfur 8%. This powder produces less smoke than gunpowder, but mixing process is quite dangerous. This aspect has prevented its extensive production and use. The fourth type is the triple base powder. The triple base powder or the propellant contains the components nitroglycerine, nitrocellulose, black powders. The percentages of the various constituents vary but do not offer any special advantage. Hence, they are seldom used. The fifth type is the RDX based propellant. It is a new propellant in which the active ingredient is from the family of cyclotrimethylene triamine, that is RDX, has come up. It is being utilized in the manufacture of cartridges by controlling not only the shattering nature of the high explosive, but also its heat production. The advantages are obvious. The rate of fire can be increased without detrimental effect on the weapon firing the ammunition. However, its composition and other details are not available presently as of now. An ideal powder should have the following features. First, it should be stable on storage. It should not be corrosive in nature. It should produce minimum amount of a smoke. It should produce minimum amount of heat for a given velocity. It should be homogeneous, that is, same amount of the powder should give same velocities. It is mainly to improve these qualities that most of the research on propellants is being done. In addition, reduction of the production cost and increase in safety margins are other important considerations that are taken care of. Consequently, new propellants are always lined up in the market. Next, we will be giving you a brief history of propellants. Gunpowder, whether it is black powder, nitrocellulose or a double-based powder, is a solid substance that on combustion is converted into very large volumes of gas within a very short period of time, whilst nitrocellulose based powders can be detonated in a small arms ammunition. They are merely propellants which on ignition produces large volume of gaseous material which propels the missile down the bore. During combustion, the rate of reaction is exponentially proportional to the pressure. Thus, unconfined gunpowder or a nitrocellulose powder will gently burn at a fairly steady rate. However, if the powder is confined within the chamber of a weapon with a bullet in the bore, the rate of burning will increase dramatically as the pressure builds up. This will continue until the bullet begins to move down the barrel. If the type and quantity of propellant have been correctly chosen for the bore size, bullet weight and barrel length, the rate of burning will proceed at a level where the pressure will be maintained until the bullet leaves the barrel. At the point at which the bullet leaves the barrel, all the propellant should have burned to its gaseous components. Propellants can be loosely divided into two classes. First, black powder and then nitro-based powders. Whilst both type of propellants are commercially available, the use of black powder tends to be restricted to enthusiasts firing muzzle loading weapons. Virtually all modern cartridges are loaded with some form of nitrocellulose powder only. First, here we will be discussing about black powder. Black powder was undoubtedly the earliest form of gunpowder or propellant used in firearms. It is, however, impossible to determine with any degree of authority who invented it. The use of Greek fire to capture the city of Delium by Beatans in 424 BC is well recorded, although it was probably used as no more than an incendiary device. The Chinese are known to have fired incendiary and explosive devices from a bow or catapult as early as 1000 AD, and their name for gunpowder was standardized by 1040 AD. This Chinese gunpowder probably spread to Europe via the Mongols under Genghis Khan. The earliest European reference to gunpowder is found in the writings of Friar Roger Bacon, who lived in England from 1214 to 1294 and prepared his manuscripts on the subject around 1250. He was familiar with his explosive properties but does not appear to have had any idea as to its use as a propellant. His formula of 7 parts of potassium nitrate, 5 parts of sulfur and 5 parts of charcoal remained standard until improved upon by the French in 1338. Another document written by an obscure monk, Marcus Gracius, also deals with gunpowder. The original portion of the document is dated 846 AD and is written in Greek. That portion dealing with gunpowder was added to Gracius' document at a later date and in Latin and is dated 1240. Roger Bacon spent some time in Spain and his knowledge thought to have originated from Marcus Gracius' document. From time to time, various changes have been made to the composition of gunpowder to make it burn faster or slower in 1781. It was found that by corning gunpowder, that is wetting it and then compressing it, then after allowing it to dry, grinding it up again into the desired grain size, a much more efficient powder could be produced. It was also found that with each successive corning, the powder improved in performance. Black powder has, due to its ability to absorb water from the atmosphere, a high propensity for ignition by static electricity and a low impact ignition tolerances, a difficult powder to store and keep. It is also due to the aforementioned properties a difficult material to have transported, and in many countries a special explosives license is required before it can be easily purchased. The second type are the nitro powders or the nitro based powders. The development of a smokeless powder was closely associated with the discovery of gun cotton and nitroglycerine, both of which are high explosives. When first discovered, attempts were made to use these nitro explosives as propellants. However, the detonation occurred with such instantaneous violence that the weapons were blown apart before the bullet even started to move down the barrel. Some way had to be found to tame the violent detonation of the explosive into a controlled and progressive burning, which would thereby produce large volumes of gas in a predictable manner. The first form of smokeless powder was probably made by Weil, a French chemist, in 1884. By dissolving nitrocellulose or gun cotton, as it is also known, in a mixture of ether and alcohol, a gelatinous colloid was formed. This can be rolled into sheets or extruded into rod or tube form. When dried, it forms a hard, stable material which can easily be handled. This type of a smokeless propellant is called as single base powder. Another form of propellant was developed by Alfred Nobel in the year 1887. In this form, the nitrocellulose was dissolved in nitroglycerine. Petroleum jelly was added as a lubricant and stabilizer, and the material so formed could then be extruded or rolled and cut into shape or size required. This type of propellant is called as the double base powder. Probably the most familiar form of a double base powder is the British military propellant cordite. This propellant was until quite recently used in all British military rifle and pistol ammunitions. Cordite contains 37% nitrocellulose, 58% of nitroglycerine and 5% of petroleum jelly. The advantages of nitro-based propellants over black powder are many and include a very small quantity of a nitro-based propellant is required in comparison to black powder. The ease with which it can be modified to it almost any circumstances. A negligible quantity of combustion residues left in the bore. The low corrosive nature of the combustion residues. The flameless temperature of ignition for nitrocellulose propellants is rather low at approximately 350 degrees centigrade. However, if ammunition is subjected to fire, it is the primer which will almost invariably ignite first, as the ignition temperature of this is around 250 degrees centigrade. Next, we will be discussing over here the color coding of ammunition. In addition to the head stamp, military ammunition often has some form of color coding in the form of bands of colored lacquer round the bullet, a stripe across the bullet case joint or round the joint between the primer and the cartridge case, that is the primer annulus. Caution should be exercised when attempting to identify the stripe of color round the case bullet joint or primer annulus, as this is often no more than a waterproofing varnish. As a general rule, if there is no colored varnish on the bullet, then it is a standard ball or a military nomenclature for the standard bullet round. Examples of colored lacquer used and their significance are as follows. First is China. Originally, China used the Russian system of color coding as their ammunition was originally supplied from the source only. In the year 1967, however, China adopted her own system, which is, first is bullet tip code. If it is green in color, then it is tracer, black and red, armor piercing or incendiary pre-1967. If it is black in color, then armor piercing or incendiary post 1967. Violet and red, armor piercing or incendiary or tracer type pre 1967. Violet, armor piercing or incendiary or tracer post 1967. If the bullet tip is red in color, then it is incendiary type, and if it is white in color, then mild steel bullet core pre 1967. For Israel, we have a table of bullet tip, primer annulus and the bullet type. If the bullet tip none color, then primer annulus is purple in color and the bullet type is ball. If bullet tip is red in color, then primer annulus is green in color and bullet type is tracer. If bullet tip is black in color, primer annulus green, the bullet type will be armor piercing. Then is black, the primer annulus is red in color and the bullet type is armor piercing and incendiary. If bullet tip is blue in color, then primer annulus is green in color and the bullet type will be incendiary. In case of NATO countries, all NATO countries use the same bullet tip color coding system, that is, for red it is tracer, for black it is armor piercing, for silver it is armor piercing or incendiary, for blue it is incendiary, for yellow it is observation, a bright flash and smoke on impact, for yellow or red observation or tracer, for orange it is dark ignition tracer. In case of United Kingdom, prior to formation of NATO in the year 1955, if primer annulus is purple in color, then it is ball or practice. If it is green in color, then armor piercing. If it is red in color, then it is tracer. If it is blue, then it is incendiary. If primer annulus is yellow in color, then proof, a special high pressure cartridge. If primer annulus is black, then observation. If the bullet tip is blue in color, then it is of incendiary type. If it is black in color, then observation. If it is green in color, then armor piercing. If it is white in color, then short range tracer. If it is gray, then dark ignition tracer. If it is red in color, then long range tracer. For United States, 7.62 cross 51 mm ammunition uses a NATO code. .30 inches carbine and .45 inches ACP uses a red tip for tracer. .50 inches Browning machine gun uses a NATO code plus. For red tip silver band, it is armor piercing or incendiary or a tracer type. For yellow tip red band, it is an observation or a tracer type. For brown tip, it is tracer type, and for light blue tip, it is incendiary. For USSR, in the 1930s, the color coding was very poor, but during and after World War II, it was regularized and expanded. The following bullet tip color code system is now a standard for all Warsaw Pact countries. If it is yellow, then heavy ball. For silver, it is light ball. For green, it is tracer. For black, it is armor piercing. For black or red, it is armor piercing or incendiary, which is now obsolete. For black or yellow, it is armor piercing or incendiary, which is being used currently. If it is purple or red, then armor piercing or incendiary or tracer. Red, incendiary or tracer type. Black or green, reduced velocity for silenced weapons. Now, dear students, let us conclude this lecture. As you have already known that ammunition comprises of projectile, primer, propellant, cartridge, case, etc. and that is why it becomes pertinent to study in detail about all of these. Apart from the various types of bullets and pellets, color coding is also given to ammunitions to know about the type of bullet.